Boredbrains Consortium is dedicated to developing and promoting adaptive, intelligent, and ethical systems based on the Mobius-inspired Cyclical Transformation, or MICT framework. Our aim is to create technology that benefits all of humanity. We address the fundamental limitations of current linear, static approaches in complex problem-solving, AI development, and system design. These limitations often lead to inefficiency, a lack of adaptability, unsustainable resource consumption, and ethical challenges.
Our solution is the MICT framework, a novel, unifying methodology inspired by natural cycles and cognitive processes. Its core iterative cycle of mapping, iteration, checking, and transformation enables systems to continuously learn, adapt to dynamic environments, and solve complex problems with unprecedented efficiency. MICT's key differentiators include its potential connection to the fundamental mathematics of complex numbers, quantum-inspired principles for modeling nuanced cognition, inherent adaptability, and a built-in foundation for ethical AI development through the Guardian concept.
The MICT framework serves as the foundation for a comprehensive ecosystem of interconnected technologies and applications. This includes MICT Action Planning System, our initial commercial SaaS product, a next-generation project management tool providing dynamic planning and AI-driven insights with an MVP in development. We also have an available module core release, which includes the core MICT logic engines in JavaScript, Python, and Rust Dev, as well as the MICT AI Ethics Toolkit, released openly to foster community and collaboration. JARVITS, an adaptive cognitive system, represents our long-term vision for a general-purpose AI assistant capable of human-like learning and adaptation. Future platforms include foundational research into MICT-based CPU, Project Mobius, and operating system, Genesis OS architectures. We are exploring diverse applications in scientific simulation, materials science, finance, healthcare, education, and social impact initiatives.
Our business model leverages a combination of revenue streams, including SaaS subscriptions for the action planning and eventual ERP application suite, tiered commercial licensing for the core framework, consulting and training services, and R&D grants. This supports ongoing development while ensuring commercial sustainability. The management team, led by founder John Reagan, the creator of MICT with over 20 years in technology and business strategy, possesses the core vision and technical expertise. This is augmented by key advisors in finance and AI, and collaboration with advanced AI like Google's Gemini.
We are seeking $2.5 million in seed funding to accelerate the launch of the MICT Action Planning app, and other systems expand our core engineering and marketing teams, establish initial operations locally and abroad, and continue research and development across the MICT ecosystem. Boredbrains Consortium offers a unique opportunity to invest in a foundational technology with the potential to disrupt multiple industries and shape the future of intelligent systems. We aren't just building software, but a new paradigm for adaptive intelligence grounded in scientific principles and committed to ethical development.
The modern world is characterized by accelerating complexity, rapid change, and unprecedented levels of interconnectedness. From developing sophisticated AI systems and managing intricate software projects to tackling global challenges like climate change and understanding the fundamental nature of reality, the problems we face demand new ways of thinking and more powerful tools. However, many of our current paradigms and methodologies, particularly in technology and scientific research, are struggling to keep pace, often constrained by inherent limitations rooted in linear, static, and reductionist thinking.
Traditional waterfall models used in software development, while structured, lack the flexibility to handle evolving requirements or unforeseen challenges. Even agile methodologies, while iterative, can sometimes struggle with managing deep systemic changes or adapting to truly novel situations without significant refactoring or process disruption. static architectures often lead to brittle systems that are difficult to maintain and extend. Many current AI models, particularly large language models, are trained on massive static datasets. While powerful, they often lack true understanding, exhibit brittleness when encountering out-of-distribution data, struggle with common-sense reasoning, and require immense computational resources for training. Their learning process is typically offline and non-continuous, limiting their ability to adapt dynamically to new information or changing environments in real time. Traditional project management approaches, like Gantt charts and critical path analysis, often assume a predictable linear progression. They struggle to effectively manage projects with high uncertainty, frequent changes, or complex interdependencies. Plans quickly become outdated, leading to inefficiencies, missed deadlines, and budget overruns. While the scientific method is fundamentally iterative, the process of research and the models used are often constrained by linear thinking. Reductionist approaches, while valuable for understanding individual components, can fail to capture the emergent properties and complex interactions within larger systems, like ecosystems, the brain, or the universe.
The limitations of linear thinking make it difficult to build systems that are truly adaptive and resilient. Current tools and methodologies often struggle with handling dynamic environments. Systems often fail to respond effectively to unexpected changes in their environment or operating conditions. Continuous learning. Most systems are designed with a fixed set of capabilities and require significant manual intervention, such as retraining or reprogramming to learn new skills or adapt to new data. Complexity management becomes an issue. As systems become more complex and interconnected, traditional design and management approaches become increasingly inadequate. Predicting emergent behavior. Linear models often fail to predict the emergent behaviors that can arise from the complex interactions within a system. Robustness and fault tolerance. Static systems can be brittle and susceptible to failure when encountering unexpected inputs or conditions.
The problems we face today, from optimizing global supply chains and modeling climate change to understanding human cognition and developing general AI, are characterized by unprecedented complexity and interconnectedness. Linear reductionist approaches are often insufficient to capture the dynamics of these systems. We need new frameworks that embrace complexity, nonlinearity, and emergence. The training of state-of-the-art AI models, particularly large language models, requires enormous amounts of computational power and energy. This raises significant concerns about the environmental impact and the long-term sustainability of current AI development trends. There is a critical need for more energy-efficient AI architectures and training methodologies.
As AI systems become more powerful and autonomous, ensuring their ethical alignment with human values becomes paramount. Current challenges include bias. AI models trained on biased data can perpetuate and even amplify societal biases. Lack of transparency, often referred to as the black box problem. The decision-making processes of complex AI models are often opaque and difficult to understand, making it hard to identify and correct ethical issues. Hallucinations. Generative AI models can produce outputs that are factually incorrect or nonsensical. Value alignment. Ensuring that AI systems consistently act in ways that are beneficial to humanity is a complex and unsolved problem.
The limitations of current paradigms, characterized by linear thinking static models, difficulty managing complexity, unsustainable resource consumption, and challenges in ethical alignment, highlight a critical need for a new approach. We require frameworks that are inherently adaptive, efficient, transparent, and capable of handling the dynamic, interconnected nature of the complex systems we seek to understand and build. This is the opportunity that the Boredbrains Consortium addresses with the MAP, Iterate, Check, Transform, or MICT framework, derived from the Mobius-inspired cyclical transformation theory.
The limitations of current paradigms do not represent insurmountable barriers. Rather, they signify a profound opportunity for transformative change. The challenges posed by complexity, dynamism, inefficiency, and ethical concerns create a clear and pressing need for a fundamentally new approach, an opportunity perfectly aligned with the capabilities offered by the MICT framework.
The core opportunity lies in the growing demand for a unifying, adaptive framework capable of addressing complex, dynamic problems across diverse domains. Organizations and researchers are increasingly recognizing that linear, static models are insufficient. MICT, with its foundation in cyclical processes, interconnectedness, and emergence, provides this much-needed meta-level methodology. It offers a common language and a structured approach for modeling systems that learn and evolve. Managing complexity through hierarchical representation, or HCTS, integrating insights from disparate fields, fostering continuous improvement and adaptation.
The practical applications derived from the MICT framework translate into a substantial market opportunity for tools, platforms, and services built upon it. This includes next-generation software, development tools, libraries, like our MICT logic engines, and potentially even MICT native programming languages that enable the creation of more adaptive and resilient software. Advanced AI systems, platforms, and services for building AI, like JARVITS, that are more efficient, explainable, ethical, and capable of continuous learning. Intelligent project management tools like our MICT Action Planning app that move beyond the static planning to offer dynamic, adaptive project management with AI-driven insights. Specialized simulation and modeling tools for simulating complex systems in fields like physics, biology, e.g., contributing to efforts like OpenWorm, finance, and climate science, leveraging MICT's ability to handle dynamic interactions. Consulting and training, providing expertise and training to organizations seeking to implement MICT principles for process improvement, innovation, and strategic planning.
The current trajectory of AI development, particularly the focus on ever larger models with massive energy demands and opaque decision-making processes, is facing increasing scrutiny. There is a rapidly growing interest and demand for AI that is more energy efficient, addressing sustainability concerns and reducing operational costs. MICT's potential for targeted processing and adaptive learning offers a path towards significantly lower energy consumption compared to brute force approaches. More explainable AI, or XAI, the structured cyclical nature of MICT, can make the reasoning processes of AI systems built upon it more transparent and easier to understand, addressing the black box problem. More ethical AI, the MICT framework explicitly allows for the integration of ethical checks and balances, as demonstrated by our AI Ethics Toolkit and the Guardian concept, aligning with the urgent need for responsible AI development. MICT is perfectly positioned to meet this demand, offering a pathway to developing AI that is not only powerful but also sustainable, transparent, and aligned with human values.
The MICT framework is not merely an incremental improvement, it represents a potential paradigm shift in how we design and interact with complex systems. This creates opportunities for disruptive innovation across multiple industries, rethinking computation with Project Mobius, the MICT-based CPU concept, aiming to fundamentally change hardware architecture for greater adaptability and efficiency. Transforming software development, moving beyond rigid architectures towards self-adapting, continuously learning software. Revolutionizing AI, creating AI that learns more like humans, understands context more deeply, and operates more ethically. Accelerating scientific discovery, providing new tools for modeling and simulating complex phenomena in physics, biology, and other sciences. Solving previously intractable problems, applying the framework to complex societal challenges like food insecurity, as explored by the consortium. The Boredbrains Consortium, centered around the MICT framework, is uniquely positioned at the intersection of several major technological and societal trends. The clear need for more adaptive, efficient, and ethical solutions, combined with the broad applicability of MICT, creates a significant and timely market opportunity. By developing a portfolio of innovative tools, platforms, and applications based on this powerful framework, We aim to not only achieve commercial success, but also to make a lasting, positive impact on the future of technology and society.
Addressing the limitations of current paradigms requires a fundamental shift in perspective. The Boredbrains Consortium solution is the Mobius-inspired cyclical transformation (MICT) framework, a novel unifying methodology designed to model, manage, and optimize complex dynamic systems. MICT provides a structured yet flexible approach that enables continuous learning, adaptation, and the emergence of intelligent behavior.
The MICT framework is deeply rooted in the Mobius theory, which proposes a different way of understanding reality itself. Mathematically modeled on the paradoxical properties of the Mobius strip, a one-sided, continuous loop, the theory posits that the universe at its various scales operates based on fundamental principles often overlooked by linear, reductionist models. Interconnectedness. All components within a system, and indeed different systems themselves, are intricately linked and mutually influential. Actions in one part have cascading effects, often non-linearly. Cyclical transformation. Change is not merely linear progression, but occurs in continuous cycles of evolution, feedback, and renewal. Systems are in constant flux, adapting and transforming. Emergence, complex, often unpredictable properties and behaviors arise spontaneously from the interactions of simpler components. The whole is truly greater than the sum of its parts, a holism. To understand any system, one must consider its entirety and the interplay of its components rather than focusing solely on isolated parts. Non-linearity. Small inputs or changes can lead to disproportionately large outputs or shifts in system behavior, challenging simple cause and effect predictions. The Mobius strip serves as a powerful mathematical foundation for these principles, representing a single, continuous entity where apparent dualities are unified and processes flow without definitive start or end points.
The Mobius theory is operationalized through the practical map, iterate, check, transform, or MICT framework, a structured yet adaptable cycle designed for problem-solving, learning, and system management. The core MICT cycle consists of 4 distinct stages: mapping, M, understanding the state and context; purpose, to establish a clear understanding of the system's current state and its surrounding context. This involves identifying relevant variables, parameters, constraints, goals, and interconnections. Function, gathering information, analyzing the situation, defining the problem space, identifying potential influences, internal and external, and preparing for action. It answers the question, where are we now? Iteration I, action and exploration. Purpose, to take action within the defined context, explore possibilities, and generate data or results. Function, executing processes, running simulations, testing hypotheses, implementing strategies, or performing actions based on the information gathered during mapping. It answers the question, what happens if we do this? Checking, C, evaluation and feedback. Purpose, to evaluate the outcomes of the iteration stage against goals, expectations, or defined metrics. This stage provides critical feedback for learning and adaptation. Function, measuring results, comparing outcomes to objectives, identifying errors or discrepancies, analyzing performance, gathering feedback, internal or external, and assessing the system's current trajectory. It answers the question, how did we do and what did we learn? Transformation, T, adaptation and evolution. Purpose, to adapt the system based on the insights gained during the checking stage. This is where learning is integrated and the system evolves. Function, updating the system's internal state, modifying parameters, adjusting strategies, refining models, implementing corrective actions, or even changing the system's goals. It answers the question, how do we improve or change based on what we learned?
Sub-variance MICT-II, also known as integrated, is a simplified version where the checking and transformation stages are effectively combined. This variant is suitable for processes where evaluation directly leads to the selection of the best outcome or adaptation. MICT/D/HQC which stands for Dimensional Human Quantum Cognition, is an advanced variant incorporating two key concepts. First, dimensionality, which represents and analyzes systems across multiple dimensions or levels of abstraction, linking to the infinity ladder concept. Second, human quantum cognition, or HQC, utilizes principles inspired by quantum mechanics, such as probabilistic reasoning, context dependence, and superposition analogies. This helps to model complex cognitive processes and decision-making under uncertainty, providing a richer understanding of human-like intelligence.
The MICT framework offers significant advantages over traditional approaches, positioning it as a foundational technology for future systems. One of the key benefits is its inherent adaptability. Unlike static models, MICT is designed for change. The cyclical nature, with its checking and transformation stages, allows systems to dynamically adapt to new information, changing environments, and evolving goals without requiring complete reprogramming. Another major advantage is its universal applicability. MICT is a meta-framework, meaning its principles are not tied to a specific domain. We have demonstrated its potential applicability across diverse fields, including software development, artificial intelligence, project management, financial modeling, scientific simulations such as the three-body problem and quantum measurement, cognitive modeling, and even social systems.
Modeling interconnectedness is a core strength of MICT. It explicitly embraces and models the interconnectedness inherent in complex systems. The mapping stage focuses on identifying relationships, and the cyclical process tracks how changes propagate through the system. Additionally, the hierarchical structure, or HCTS, is another key feature. The ability to nest MICT cycles allows for the modeling of complex systems at multiple levels of abstraction, from individual components to the overall system behavior. This provides a scalable and organized approach to managing complexity.
The MICT/D/HQC variant offers a novel approach to modeling systems exhibiting uncertainty and context dependence, drawing inspiration from quantum cognition to potentially create more nuanced and human-like AI. Our research has revealed a compelling alignment between the mathematical structure of complex numbers and the MICT cycle. The rectangular form, A plus bi, can be interpreted as an abridged MICT cycle, while the polar form, R times the quantity of cosine theta plus isine theta, reflects the full dynamic process. This suggests MICT may tap into fundamental mathematical principles underlying physical reality. MICT facilitates the integration of ethical considerations. The checking stage provides a natural point for evaluating outputs against ethical guidelines, incorporating human oversight, the guardian concept, and triggering corrective actions in the transformation stage, enabling the development of more responsible AI systems.
The MICT framework is more than just a methodology, it's a new way of thinking about complex dynamic systems. Its adaptability, universality, and deep connections to fundamental mathematical principles make it a powerful solution for the challenges of the 21st century. It provides the foundation upon which the Boredbrains Consortium is building a new generation of intelligent, adaptive, and ethical technologies.
The theoretical power of the MICT framework is realized through robust software implementations and development tools. Boredbrains Consortium is actively developing a suite of technologies designed to make MICT accessible, practical, and impactful.
The foundation of our technology stack is the core MICT logic engine, providing the fundamental implementation of the MICT cycle. This engine is designed to be lightweight, flexible, and easily integrated into various applications. JavaScript implementation. It is complete and well documented using JS-Doc. It's a robust implementation of the MICT class, suitable for both front-end and back-end JavaScript development. It includes features for managing stages, stage functions, automatic and manual cycling, and error handling. This makes it ideal for web applications, interactive simulations, browser extensions, and Node.js Dash-based services. Python implementation. The is also complete, well documented with docstrings and type hints. It's a Python counterpart to the JavaScript engine, offering the same core functionality. It's ideal for back-end development, data science, AI/ML applications, and scientific simulations, leveraging Python's strengths for numerical computation and integration with popular AI libraries, suitable for server-side applications, AI model training and inference loops, scientific computing and automation scripts. Rust implementation. Currently under internal development, this high-performance implementation leverages Rust's focus on speed, memory safety, and concurrency. It's targeted for performance-critical systems including Genesis OS, Project Mobius, robotics, and embedded systems.
The JavaScript and Python core MICT logic engines are released under the Boredbrains Consortium license. For non-commercial use, these engines are free for personal learning, academic research, education, and internal company use that doesn't generate revenue, with attribution required. Knowledge sharing is required back to the consortium for cycle cataloging. For commercial use, a commercial license is required. Terms and conditions to be discussed based on usage and involvement. A separate commercial agreement is required. For more details, please contact us.
Recognizing the critical importance of ethical considerations in AI development, we have released the MICT AI Ethics Toolkit as a separate project. The purpose of this toolkit is to provide developers with practical tools and examples for integrating ethical checks and balances into their AI systems using the MICT framework. The toolkit includes reusable functions in JavaScript and Python for specific ethical tasks, such as bias detection and hallucination detection. These functions calculate metrics like disparate impact and perform basic checks for factual consistency in LLM outputs. The toolkit also provides MICT integration examples with concrete runnable code demonstrating how to use these functions within the checking and transformation stages of a MICT cycle to monitor and mitigate ethical risks. It's released under the Boredbrains license for use as indicated. This toolkit directly addresses the growing need for practical tools to build fairer, more transparent and trustworthy AI systems.
Understanding and debugging complex, interconnected MIT cycles can be challenging. To address this, we are developing the MICT HCTS Visualizer tool. The concept is an interactive development environment, or IDE, and possible VS Code extension, designed specifically for MICT-based systems. Planned features include visual 3D cycle representation, which dynamically visualizes MICT cycles, their stages, states, and interconnections. Real-time monitoring will display the current stage and state of running cycles in real time. Code integration allows you to view and potentially edit stage function code alongside the visualization. Debugging tools will let you step through cycles, set breakpoints, and inspect state. Configuration management will enable you to visually create and configure MICT cycles. Hierarchical 3D visualization will support visualizing complex HCTS structures. This tool is crucial for accelerating development, improving understanding, facilitating debugging, and making the MICT framework more accessible to a wider range of developers. It turns an abstract framework into a visually intuitive development process.
The MICT framework is designed to seamlessly integrate with external AI services and models, particularly within the iteration and checking stages to enhance system capabilities. The mechanism is straightforward. Iteration stage functions within a MICT cycle can make API calls to services like the Google Gemini API or other large language models and vision models. In the checking stage, applications include analysis, where AI analyzes data generated during the iteration stage, such as analyze these simulation results for anomalies or evaluate the sentiment of this customer feedback. Validation uses AI to validate outputs against complex criteria like check if this generated code adheres to security best practices or verify the factual accuracy of this summary. Risk assessment employs AI to assess potential risks based on the current state. In the transformation stage, AI can be used for recommendations, generating suggestions for how to adapt the system, such as suggest alternative strategies or recommend parameter adjustments. Automated actions involve AI generating code or configuration changes to implement adaptations. Content generation uses AI to create reports, summaries, or other outputs based on the cycle's results. The benefits of this integration are significant. It allows MICT-based systems to leverage the powerful pattern recognition, knowledge retrieval, and generation capabilities of large AI models, significantly enhancing their intelligence and adaptability without requiring the development of these complex models from scratch.
Our technology stack, centered around the versatile MICT framework and implemented through core logic engines, specialized toolkits, and planned visualization tools, provides a robust foundation for building next-generation adaptive and intelligent systems. The open code nature of key components fosters collaboration, while the planned integration with powerful AI services amplifies the framework's capabilities. This combination enables us to tackle complex problems across diverse domains in a uniquely efficient, adaptable, and ethically conscious manner.
The true power of the MICT framework lies in its universal applicability. It's not just a theoretical construct, but a practical methodology for building a wide range of adaptive and intelligent systems. Boredbrains Consortium is actively developing a portfolio of interconnected projects, creating a synergistic ecosystem centered around MICT.
Our initial product is a next-generation project management and action planning application. Unlike traditional static tools, this system leverages MICT to provide dynamic planning, adaptive task management, and real-time progress tracking. Users define goals, and the system helps break them down into manageable steps, monitors progress through iterative cycles, provides feedback, and facilitates adaptation to changing priorities or unforeseen challenges. Currently, it is actively under development in the minimum viable product phase. Key features include project and task creation, MICT cycle management for tasks, user authentication via Stitch, and a React-based front-end connected to a Node.js/MySQL backend. This application serves as a concrete demonstration of MICT's value in a large and established market like project management software. It provides a near-term path to revenue generation and user adoption, validating the framework's practical benefits while funding further research and development across the consortium's portfolio.
JARVITS represents our long-term vision for a truly general-purpose, human-like AI assistant. Built entirely on the MICT HCTS framework, JARVITS is designed to be more than just a language model. It's an integrated cognitive system capable of understanding context, reasoning, planning, learning continuously, and interacting with the world through various modalities. Potential capabilities include deep language understanding, processing and understanding complex natural language requests and information, visual perception, analyzing and interpreting images and potentially video, code, understanding and generation, assisting with software development tasks, continuous learning, adapting its knowledge and skills based on new information.